to the next session here on root locus plots. This is a particular type of control system analysis to determine whether we've got stability, a system's unstable, or in some instances, neutrally stable. What I'm going to do today is introduce the concept of what root locus plots are, give you the basic understanding how we analyze them, calculate concepts based around open and closed loop transfer functions. So basically, it's the fundamental concept of how we instigate a root locus plot at the fundamental level. I do say successfully draw one. It's going to be done in MATLAB very quickly, and then go through the 9 rules associated with the root locus. Right. To begin with, there's a couple of things we need to point out. Right, so the root locus is a tool, as you can see there, designed to graphically represent how a system changes, what the roots of a system changes, as we go from open loop to closed loop. And by doing that, we change the gain, or the adjustable gain in that system, from 0 to infinity. So as we change this value of k, the root's value changes by a set value. It will move along a plot, and at some particular points, it may go from stable to unstable. Right, obviously the roots, you can see there in the paragraph above it, says the value of those roots is significant in determining stability. There's 2 quick concepts to run through. It's not drastically important for this session. It's just to be aware of where the formula comes from. This is something you can do in a lot more detail elsewhere. So the gain can be placed in 2 locations. You can see here it can be in the feedback path or the feed forward path. So forwards, obviously got our inputs, goes to a system. There's the adjustable gain. We are in control of this. We can modify this value. Out it goes, we get our inputs. In some instances, you may find that this gain value is in the feedback path. So if this output isn't particularly as desired, it goes to the feedback, gets corrected, ready to come back out at the desired level. Right. In a simple system, we can introduce something called the open loop transfer function. So open loop will typically not have this section, the fundamental concept. So GH is the open loop transfer function. Right, and what you can do is close this off to form a closed loop system. This is often written in 2 ways. It's either written like that, or GH equals 1. The basic is rewritten with that equation. This one is the closed loop transfer function. Right. That is the basic concept that you need from block diagram concepts. That's all you need to begin to analyze root locus plot. So GH represents the open loop transfer function. GH just bear with me. You know, make sure I'm doing this bit little bit right. Looking for the GH. Yeah, that should be +1. Sorry, equals -1. Thought there was an error there. Right. So open loop GH equals the open loop transfer function. We'll analyze what that is very shortly. GH +1 or GH equals -1 is the representation in simplistic form for the closed loop analysis. Right. Starting with the open loop transfer function then. So in that last little discussion there, we had GH, representation of open loop transfer function, abbreviators here to OLTF, open loop transfer function. And this nasty little equation is a little bit easier to understand once you get your idea of what's going on here. When we analyze a system, we start with the open loop transfer function. The first thing we're going to do is analyze the numerator separately and the denominator separately. Right, so basically it starts off analyzing the top or the numerator. If we put in a value for S, probably able to do a different color. You put in a value for S, you add this particular value, it should equal naught. So basically this is the individual systems of a control system. So we'll see here, little example, you might get block like that. And then another block. Or goes, you can have your feedback somewhere. It's very basic system, right? So here we've got a numerator. It'd be a case of if you put in a value for S, you add 1 to it, and this equals naught. So what is that value? Obviously, in this particular instance, it should be right. Because that was a numerator, it's not divided by anything. That would represent a 0 in our system. You can do the same with the denominators. So if you look in this second block I've drawn very quickly, we've got a numerator and a denominator. The top one says S plus 2. So it's the same principle. If you put a number in for S, you add 2 to it, it equals naught. So the output should be minus 2. Again, that's a 0 because it's on top. This S minus 3, or the denominator, is the same principle. If you put a number in for S, you take away 3 from it, what do you get? In this instance, S should be 3. But because it's on the bottom of the fraction, we identify a pole. That is always the first step we do when analysing a system. Now, the rest of it, the capital Pi, we'll worry about very shortly, along with the K. So this is just analysing the control system transfer functions in terms of the S domain, the time domain, obtaining the zeros, obtaining the poles. Right, little example here. I'll give a pause for a couple of seconds so you can have a go, and then I'll go through the solution. Right, in this particular system, the open loop transfer function, or GH, is, if you remember from the form before, K was on top of on that formula. Doesn't really play any significance here. Obtaining all the numerators or values on top in each individual block, we get 20, 48, S plus 1, and then we're back to the start. Dealing with the denominators of each block, so this is separating the blocks out, and then just taking the denominator, so we've got S plus 20, S plus 2, 4, 6. Into this last block, we've got S plus 10. Right, it's a case of obtaining the numerator and denominator, or the zeros and poles. These two are just multipliers, so we'll magnify the response. The only value we're interested in the top initially is this s plus 1. So if you put in the value for s, we add 1 to it, it needs to equal 0. So we've got a 0 because it's on top. A 1. So minus 1. Right, on the denominator, we've got the poles. We've got minus 20, minus 2, minus 4, minus 6, and minus 10, because it's the same principle. You put a number in for each bracket, has to add the value to it equal 0, so basically the reverse of the value inside. So we go out in order, minus 2, minus 4, minus 6, minus 10, minus 20. Right. That's the solution to begin with. Obviously, it's going to get a little bit more complex than this shortly, but first thing we need to do is analyze the zeros and poles. This is going to be the start and end point for our system. Couple of things to point out. Now we've got a system to look at. The numerator often refers to the amplitude of a system. So what I mean by that is if this particular control system is oscillatory, it might have something that looks a little bit like that. This numerator affects how high or the amplitude of these waves. The denominator, so all these poles we've obtained are actual roots of a system. Effectively affect the stability. So because this is, I'm going to take an aircraft slant on this. Mainly, we're going to deal with power force systems. So if this is the longitudinal axis, we would have a phugoid. It would have two roots because the phugoid is a squared-based system. It also have the short periods. So that's the square-based system. So obviously a square times a square gives us a power 4 output. Right, so just be aware the amplitude is driven by the numerator, the actual output or the roots, the stability of your system, typically driven by the denominator. Right, next example. Again, just pause for a couple of seconds to give you a go. Right, same principle. Open loop transfer function. Numerators, okay, always on top. We've got 15, 16, and S. On the bottom, S plus 15. S squared, 4S plus 16. And S plus 10. Right. Same principle as before. I'll do the easy ones to begin with. So numerator is the zeros. There's only one to deal with, which is this bit here. If you put a number into that bracket, it needs to equal 0. There's nothing adding to it, so our 0 is actually our naught. The poles, Right, the poles, we've got this first one, do the easy two first. So we've got minus 15 and minus 10. This middle bracket needs a bit extra thought, and it's a quadratic because we set to 0. So effectively looking at something that looks like this. If you take a close look at it, it doesn't factorize. It needs the quadratic formula. So S will equal the quadratic formula minus B plus or minus the square root of B squared minus 4AC all over 2A. Right, so if you quick recap, might be no since you've seen it. B is the S term, so it's plus 4. So that will be minus 4. (16) take away 4 times 1 times 16. All divided by 2A, which is 2. Right, I'm deliberately doing it by hand because what you'll find is this square root is negative. So effectively abbreviates down to minus 4 plus or minus square root of minus 48 all over 2. Right, obviously if you try taking the square root of a negative number, you calculate it will more often than not give you a maths error. Right. Best thing to do then is we're going to break the square root into two things. Square root of minus 1, which is multiplying the square root of 48. Right, and if you've not met this before, I will go through it later in this session, but for now, all you need to know in this instance is the square root of minus 1 is abbreviated to J in engineering or I in mathematics. So this section is going to become J. This section, I'm going to break it down into something else. What I need to do is list all the square numbers up to 48. So we've got 1, 2 squared being 4, 3 squared being 9, and so on, 16, 25, 36, 49. Right. Obviously, that's too high, so we can discount that. What we're looking for out the rest of them is a number which multiplies into 48. So if you take 48 divided by one of these square numbers, it should give you a clean output. Obviously, 25 doesn't. 36 is too high for it. 16, you times that by 3, you get 48. So we've got, we're not a space here, but we've got minus 4 plus or minus the square root. Right, 48 is getting split into 16 times 3. We're taking the minus 1 as J, all divided by 2. Right. The reason I've done this under the square root is we can physically take the square root of 16, and hopefully we know that's 4. So we're getting minus 4 plus or minus 4. The J typically sits in front when it's imaginary, so let's say J4 square root of 3 all over 2. And if we to finish this off, we've got -4 and 4 on top, dividing by 2. Each of these is divisible, so we can simplify our answer. 2 minus 2 plus or minus J2 root 3 is a final output. Right, so there's two answers here. Got a pole -10, a pole at -15, a pole at -2 plus J2 root 3, another one at -2 minus J square root of 3. Right. At the moment, probably doesn't mean much. We're just getting values out. What did that actually mean? This is where I'm going to go very shortly. But for now, these are going to lie on the axes. If you plot them, it's just got a real component. And eventually going to plot a graph that kind of a graph that looks like this. So for the poles, we've got -10, -15. And then you've got these two, which will be -2 for the real component. And then this imaginary aspect. And because the signs have swapped over, it actually moves that way and that way. So it ends up symmetrical. So we get a point there and a point there. So you got 4 clear poles. Right, that is the final solution. That is a bit of extra information for number 2. Right, what we're going to do now, we've done the open loop transfer function. We've obtained the zeros. We've obtained the poles. We then close the system off and deal with the closed loop. Right. In principle, the closed loop transfer function said the open loop plus 1 equals 0. And the open loop transfer function, based on what we've been doing, is abbreviated to this. Right, so quick substitution. And then I'll very quickly explain what's going on with all of this at the top. Right, I'm going to linearize this equation, which basically in this instance means they're going to multiply up by this. Right, so there we are. Right. All that does is it clearly defines where the poles are, zeros are, and the impact of the gain here. Right, going back to the top, get rid of the scribbles. This symbol tells you you're going to multiply all the numerators or brackets with zeros in. So it's effectively what we've been doing for the last two things. So it's telling you the first bracket might look like that. So for the 0, s plus the 0 value starts at 1. So I starts at the first value. And it'll keep going depending on how many you've got. Said 3 until you get to the very end, which will be s plus zm. Right. Same for the poles. It's a slightly different notation. And in this key thing is don't mix up this j being imaginary. It's just a notation in this instance. Right. What we're going to do is take this equation, have a very close look at it. What does it actually mean? Right. If you read the top, if you set the gain value to a 0, you are effectively producing the poles only because you've got this block is getting added to all of this. And this 0 is effectively cancelling everything out. Anything times 0 is 0. So this, when the gain is set to be 0, this section doesn't exist. So we obtain the poles. Now, if we start increasing this value of gain, such that it becomes extremely large, as you can read in the second paragraph, becomes extremely large, i.e. infinity. This section becomes effectively the output because by adding the poles, which will be very minimal, they'll be negligible, we can discount this value. When the gain's extremely high, we have the zeros. What we need to do now is, obviously, we get the poles and zeros by setting k as 0, k to be infinity. What we then need to do is put in some values for k when it's not 0 or not infinity. So in other words, somewhere in between, just so we can get a grasp of what's going on. What MATLAB will do, which I'll show you very shortly, is it effectively sets every value of k from 0 to infinity, so you get the full plot. What I'm going to do is just show you a few distinct points so you get the grasp of what it's doing, how the plot moves. But remember, MATLAB is doing every single possible value for k. Right. Pick this one because we know the answers to the denominator. And obviously the numerator is very straightforward. So there's the open loop transfer function. We would have zeros, get -2, -4, -6. And obviously the poles on the bottom, we worked this one out in the last example. Right, so what I'm going to do is plot those first. So these are the limits. So you effectively get a little plot that looks like this. Real on the x-axis, imaginary on the y. Right, the zeros are in red. So we had -2, -4, -6. The poles were at -10. And then we had the -2 with the imaginary components. Right. They're the starting points. Doesn't tell you anything for now, but that is how the system is going to start and end. What does it do in between becomes important because we take them out for now. If your root or your output falls in this section, so notice it's left of the imaginary axis or the y-axis. So we've got a negative real part. The system is usually deemed to have been stable. If it falls to the right of the imaginary axis or the y-axis, so it's got a positive real part, we will have an unstable system. which kind of implies there's going to be this magic point on the y-axis where it goes from being stable to unstable. So at this particular point where the real value is 0, it's neutral stability. Right. What's the significance of all of that? Basically, you may have a k value to be stable. As you increase the k value, it may move and move and move, become neutrally stable to unstable. So you may be interested in finding what value your gain can be to ensure your system is stable. Right, so moving on with this example, we've got our closed loop transfer function, just basically bringing that denominator up. Right, the way this is going to work is we've had the value for k to be 0, k to be infinity, which we plotted. It's now a case of you set any value k you want, get the roots out, plot them on the plot. In this particular example, I've set the roots to be 2, 10, and 40. Right, so when you substitute k to be 2, the way this would work is you put 2 into that, you would expand all of this, multiply by 2, add it to the expansion of this, and then find a root solver on your calculator or MATLAB or Wolfram Alpha or something like that. And you get your S values out, which you would then plot. So in this instance, when k is set to be 2, we put a 2 in for k. I've expanded all of this, so we get an S cubed term. Added to this, which remains as S cubed term, hence we get 3 answers out. Stuck the final equation into root solver and got the values of S out. It's the values that are more important for this section here. So got 3 values to show you. K being 2, K being 10, K being 40, and it's a case of what happens to the poles or the roots when we go from K to be 0 to 2 to 10 to 40. Right, so remember the red ones being the zeros, blue being and K equals infinity. We'll put the values on initially. Right, so this will come on as an animation shortly. But what happens is if you take this section here, K equals 0, K equals infinity. So what's happening is you can clearly see as we increase the value K, the roots are moving in that direction. You've got 3 distinct branches here. It's a case of it being symmetrical. So this one goes around like this. And then it's a case of just go that way or like that. Right. 3 distinct lines are visible. So if I get rid of the scribbles I put on, a bit more accurate. You can see how the plot moves. In this particular example, it stayed stable all the way through. So it's a good design if you want it for an aircraft. You can see, as I say, from 0 to 2, 10 to 40 to infinity in this one. This is the most obvious one to look at. Now, it's a good example in the aspect that if this branch, as it's called, was over here, it may clearly go stable, neutrally stable, unstable, as it moves with the value k. Okay, right. What I'm going to do is do a final example, explain all of this, and show you the 9 rules involved with this as well. So, right, the example, I just jumped to the example first. So here we are. Right, so right. Question wise, the first thing it asks for is to sketch through Locus plot. Basically, in this instance, it means go on MATLAB and do it. So the first thing we need to do, if you have a close look at the system, we need to expand the denominator so we know what its actual function is. So expand the bottom brackets. Gives us 2s squared plus s plus 2s plus 1. Second like terms gives us 3s. Right, that is multiplied by the third bracket. X cubed. 2s squared. 9s squared. Plus 3s. Plus 3s. Plus 1. Right. So you have to do this just so you can get the denominators to plot in. There is a function on MATLAB that'll do this for you, but this is just to prove the purpose. And I do need this later on anyway. Right, so the denominator simplifies to 6s cubed. 11s squared. 6s plus 1. Right, so first up, I'm going to plot the root locus. The denominator is going to be the coefficients we've got on top and the bottom. So the values I'll end up typing in will be in descending order of powers, 6, 11, 6, and 1. Just be careful if you do have missing power, you have to put a 0 in. So, for example, this is just a little bit off topic, for example. If I had like that, my coefficients would be 6, 0, because there's no s squared term, then 6 and 1. Just be careful if there's a missing term that you have to put the 0 in. If you don't do that, and you go 6, 6, 1. It'll actually read it as 1, 6s, 6s squared. So just be a little bit careful with that. Right, plotting the plot, doing the root locus plot then. Into MATLAB, best thing I'm going to do is, it's just a control system, so I'll set the variable. Right, next bit is TF, because I wanted to recognize the fact it's a transfer function. In a set of round brackets, I'm going to put the square brackets for the numerator. There's nothing on top, so I'll set that as 1. In another set of brackets, square brackets, is the denominator. So remember, the coefficients were 6 s cubed, 11 s squared, 6s, 1, and close that bracket off. Right, so that's an identifier turning this into a transfer function. So it's time, it's in its time domain effectively. It's got numerator, clear denominator. And then it's an instance of, with that transfer function, what do I want out of it? I need a root locus. So it's going to be locus to produce the plot. System. And then want the grid on. Right. Run it. Just save it somewhere. Busy. Right, there we are. 2 seconds. So in the output, there's our system. You can see the denominator. This is an important thing because we're analyzing the roots anyway. It then churns out the root locus in MATLAB, as we can see here. Is right. In the example, it then says go through the 9 rules of the root locus plot. So I'll read them on the PowerPoint and show you how they apply, if they apply. Right, rule number 1. The number of branches to a root locus is equal to the number of poles. Right, so this is probably easier seen in this one. Poles, remember, on the bottom, zeros are on top. We've got pole number 1, pole number 2, pole number 3. Right, and I'll actually do this. So rule number 1, our poles are going to be at -1. S is also -1, but it's got twice the value. So this one ends up being at -0.5. And with this one, it becomes -1/3. Right, so spread those numbers in lines into the plot. Got a pole at -1. Got a pole at -5. And a pole at -1/3. So that verifies the poles that we've got, and it also verifies the fact we've got 3 poles. We've got 3 distinct branches: the green, the red, and the blue. Right. Rule number 2, talk about root migration. So the root locus begins at the poles. So the 3 values I've identified there. Just get rid of them 2 seconds. Right, so we're starting at -1, starting at -1/2, and we're starting at -1/3. So the 3 distinct crosses. And it moves to infinity, which is pretty obvious from what we've been through. The number of branches gone to infinity is the number of poles minus the number of open loop zeros. Right. Rule number 2. Number of poles minus number of zeros is equal to the number of branches that will just travel off through infinity and just keep on going and going and going. Right. In our system, we've got 1 pole, 2 pole, 3 poles. We've got no zeros, so all three of these branches should go to infinity. Number 1, number 2, number 3. So all 3 just keep on going. Right, rule number 3. A branch of the root locus is on the real axis if it is to the left of an odd number of poles and zeros. Right. Take a screenshot of this. Right. Branch of the root locus is on the real axis if it's to the left of an odd number of poles and zeros. There's no zeros, remember. 1, 2, 3 means this has to be on the real axis. Because obviously 3 is an odd number. Number 4 speaks for itself. The root locus is symmetrical about the real axis. Not much to it. But if you look at our root locus here, you can clearly see if I put the ruler on. It's symmetrical on the top, is on the bottom. Right. 5 and 6, I'm going to do the calculations for and then prove it because it's a case of that they're connected. Right, so number 5 says the angle of asymptotes. So all 3 of those branches go to infinity and there'll be an asymptote for each of them. The angle of that asymptote is calculated by this. So in that column. I don't think I need it that big, right? I'll just handwrite this one. Right. So rule number 5. The asymptote angle formula says plus or minus 180 to n plus 1 right. Remember, hashtag is for number, not tagging anything in for social media, unfortunately. It's just the number. This particular formula starts when n equals 0 and goes up. And there's a little trick with this one, explain as we go through. So n starts as 0. On the bottom, we've got 3 poles, no zeros. You stick that into a calculator, it should come out as 60. We increase n by 1. Again, stick that in the calculator, we get 180. Right. The general rule here is if you've got number of branches you've got is the number of times you have to calculate this. So we've got 1, 2, 3. Because the idea here is if we do the next value of n, where n would be 3, it would go beyond 360 degrees and start at the next value where the pattern continues, which will be about 420. So you only need to do this formula as many times as you have branches. So there's 3 branches, 3 values of n. Right, so that one comes out 100 degrees. Right, keep them in the bank for the next one. That is asymptote, so all those asymptotes will meet at a common point, and that common point is the centroid. So it says the sum of the poles minus the sum of the zeros over the number of those that we have. So right, so the center point is sum of poles sum of the zeros, number of poles, number of zeros. Right. We've already worked out the pole values. So the values that we had were at -1. We had one at -0.5. We had another pole at -1/3. There's no zeros to worry about. Nothing to add up for that one. We've got 3 poles and no zeros. So our centroid minus 11 over 18. Doesn't mean anything because we need to plot this in the graph to show you this. That's about minus 0.611. Right. Show you this on the graph then. Minus 0.611. This is just going to be very approximate to show you, but 0.5. Let's put it about there. Right. So we had 3 asymptotes. Right, bit off with my centroid here. Like the 180 is the easy one. So at 180, there we are. Asymptote number 1. The other two, 60 and 300s. So it might be a little bit off with the centroids, probably a bit closer that way. 60. Yeah, definitely off with the centroid location on the graph. As I said, it's been done very quick, but the idea would be that should move it that way, but where it might be closer. Should have been about there. Again, pretty far away, but you get the gist that the centroids should have been the point of interception for all of these asymptotes, and that black line should be close to each of these branches, but should never touch, or point of an asymptote. But that is the concept of Rule 5 and Rule 6. Bit badly drawn. Right. Rule 7. Like Rule 7 doesn't particularly apply in this one. We move on through later 9, it's like the more complex ones. Right. Rule 8 talks about the root locus intercepting the imaginary axis. So at what point is the gain value going to be set where this particular branch goes from stable to neutrally stable to unstable? So there's going to be a set K value at which this point will be stable or unstable. So looking for the point of neutral stability in this system. Right. This is, if I just jump back into PowerPoint, basically this bit here. Write down the characteristic equation and produce a linear equation and then make the substitution. So the first 3 points, pretty much a couple of lines there. Right, the equation says K. I'll use the expanded version just for simplicity, but right. Our transfer function of the control system started off like that. We use the closed loop version. Step 2 says produce a linear based equation. In other words, make sure there's no denominator in this. So this is simple as multiplying up by the denominator. Right. Next up is the insertion of wherever S of P is, J, omega. So J being the square root of -1, omega being the frequency response. Right, so 6. This slots into the brackets where S is. It's important that you do this. Right. If we expand it, just so to see what we've got 6. Eleven. Right, from the theory of imaginary numbers, this is in our PowerPoint here. You can see what J squared, J cubed, and J4 equal. So J is just the square root of -1. That stays as it is. If you square that, it comes out as -1. So that's going to be wherever J squared appears, we're going to put -1. Based on indices, J cubed is J squared times J, which is -1 times the square root of -1, which means J squared is J squared times J squared, which is -1 times -1, which equals +1. Right. In this particular example, we don't have a power 4. What we do have is J squared. So where J squared appears, now the easy bit. So J squared is -1. That sign swaps from plus to a minus. There's nothing on this bit. Still got K. Right, and then this J cubed term, we've got -1 times the square root of -1. And based on that notation, is that on minus J. And so we're getting minus 6J omega all cubed. Right, based on the PowerPoint, that is up to step 5. Step 6 is split that equation into its real and imaginary components. So two separate equations come out with this. We've got a real equation, an imaginary equation. It's just based on the labels here. So anything that doesn't have a j term in is deemed to be real. Okay. Minus 11 omega squared plus 1. Right. We just jump back 1 second and made a minor omission. Now just spotted. Doesn't affect too much. I just missed the 6s off, so that becomes 6 j omega plus 1. Based on the labeling, just inserts. Nothing's changed there, right? It's just so it's realized when you get to this bit, when you split this equation up, there was something missing. Right, we've got real, no j term on that one. There's no j term on this bit or on the plus 1. These two have their j terms still attached. Right, so we've got minus 6 plus 6. Right, whole concept here is we need a value of k because this is the value where the gain turns the roots from stable to unstable. But we've got this unknown in there, so we're going to have to deal with this equation first. Dealing with the imaginary equation we've got, first thing I'm going to do is divide through by 6j leaves us with minus the frequency cubed plus the frequency equals 0. We need a value for this, so what we've got is with factorizing. Right. Two solutions. One is if you insert 0 in for a frequency at that point, obviously it multiplies all of that, comes out as naught. So one of the solutions says frequency to be 0. The other one is analyzing the brackets. Got that. So rearranging says the frequency squared should equal 1. Hence, the frequency is the square root of 1. When you take a square root, you get two answers out of that, plus and a minus. Right. All of them will insert into the real equation to get our gain value. Right, so K, this is rearranging this. K is 11 down to frequency squared. Take away 1, all on the other side. Inserting the 0 first. I'm going to get the k value to be -1. Talk about that in a second. Right, this one doesn't particularly matter because you're going to end up squaring it. Right, so 11, take away 1. K equals 10. Right. Our first value doesn't exist. K has to be equal to or greater than 0. You can't have any negative gain, so that discounts. So what this is telling us, gain's 10. The system should be neutrally stable. Right. And verify that, yeah. Right. The blue branch is on the real axis. It's left to the imaginary plane, so that doesn't have any impact on what we're looking at. We're going to analyze the red and the green. Right, move this data point to the imaginary axis intercept. Should be about that. Make a bit easier, we'll zoom in on it. Right, gain, you can see, is 10. The other thing to point out, obviously, the pole split into two, but it's that the real part is insignificant and so small. Examine the imaginary part that says plus 1i or 1j. On the other branch, symmetrically remember, gains 10 again. Insignificant real component, -1j. This was this value we've been slotting in. Plus 1j minus 1j because we end up squaring this. So that verifies our solution. Which leaves us rule number 9 to finish off. I'll just replot that for simplicity, right? Yo. Rule 9. There are points on the real axis where the root locus breaks away and basically become complex. So that is this bit here, where the green and red branch goes from the real axis into its point of symmetry. Just leaving the real axis has now got value for y. That particular location is determined by solving the gain when in the closed loop situation we differentiate and solve the roots. So rule number 9, just to finish off. Right, start at the same point. Closed loop function. We linearize that as usual. So the first step's the same as before. K plus 6s cubed plus 7s squared. Right. Rearrange this for K. Because we're going to differentiate in terms of K. All of these slot into the right hand side, so it's minus values. Right, differentiating then. How it comes down, multiply, so we end up with minus 18s squared minus 22s minus 6 and minus 1 that disappears. Right, what you do now is get a root solver. So I can stick this into the quadratic equation because we set that equal to 0. So quadratic formula minus b, so it's minus 22. B squared. Make sure that goes in the brackets. Again, you can do that on MATLAB if you want to get root solver. But you get two answers out of this. Does solve nicely, believe it or not. Minus 0.811. Minus 0.411. Right. Remember, this is the point where the branches move across and start to dissipate or remove themselves from the real axis, so it's got an imaginary value as well. Right, so the blue branch doesn't go off at any particular point, so there's no need to analyze that one. Move that. Which, if we then have a close look down here, data point minus 0.411. Do the same with the green, minus 0.411. So out with the two solutions. That is the point of breakaway. Right, that verifies or runs through all of the 9 rules for the root locus plot, shows you how to verify them on MATLAB and the respective plots. And the key point, remember, the point of imaginary axis is the point of stability typically. So anything to the left of the imaginary plane is stable, anything to the right of that is unstable. This particular point is the point of neutral stability. We've also got amplitude on top, stability on the bottom. Right, that concludes the session.